Good morning, everyone. I would like to discuss our work on the question of second sound in germanium, and let's jump right in. So we start where Hardy left off. Where did Hardy leave it exactly? Well, using approximate solutions to the linearized Boltzmann transport equation, Hardy established that we could think of second sounds in three categories. The first, the one we're most familiar with, is drifting second sound, wherein there's this imbalance of normal and umklapp scattering that create conditions for this wave-like transport of temperature. And this has been observed in sodium fluoride, bismuth, and graphite in different experimental geometries. Hardy observed that under certain conditions determined by the collision matrix, there would be the existence of this driftless second sound that does not require this imbalance of normal and umklapp scattering. And finally, Hardy left room for other types of second sound, wherein the slow energy flux relative to the heating frequency would yield the observation of wave-like transport of heat. And this is recently proposed to be satisfied in the frequency domain thermal reflectance geometry. To capture these second sounds from a microscopic perspective requires solving a linearized Boltzmann equation. And we've devised a method for doing so. You can see the details in this paper here. And we have an advantage that Hardy did not at the time, and that is that the collision matrix can be constructed from first principle calculations. And so that allows us, by solving this equation, to capture all of these different types of second sounds. And so we're going to review the proposal from Beardo and al., wherein the frequency domain thermoreflectance experiments on transducerless germanium were observed to deviate from the Fourier regime and subsequently captured by a hyperbolic heat equation. So what goes on in frequency domain thermoreflectance is that you modulate a heat source. In this case, it's a laser, and you track the reflectance via a probe laser that captures or encodes the relative oscillation at the temperature due to the periodic heat flux. And so you can track the phase between the surface temperature and the heat flux and model it according to your choice of models. And what Beardo and al. Observed in the case of germanium was that there is this deviation at high frequencies that was captured by the hyperbolic heat equation. And so where we are interested in what we're interested in working on is to understand this from a microscopic perspective. Do we predict a wave-like behavior in the temperature profile in germanium from microscopic theory? And to do this, we'll work our way through Hardy's three categories of second sound, beginning with drifting second sound. So the properties for the work that you're seeing here were previously validated independently in the TT geometry, wherein we do see deviations from the bulk thermal conductivity even at gratings periods of 10 microns at room temperature. So using those properties, we can verify our Geyer condition for the hydrodynamic window. And if we only consider umklapp scattering in a pure sample, we see that there's this very narrow hydrodynamic window at low temperatures. But as soon as we consider any sort of small amount of isotopes, this hydrodynamic window disappears, making it essentially practically infeasible to observe this type of drifting second sound in germanium. Going on to driftless second sound, we need to perform this eigenvalue decomposition of the collision operator. Remember that now we have the first principles input to construct this eigenvalue problem, whereas Hardy did not. So we can actually check whether the condition for driftless second sound is satisfied for a given material, in this case, germanium. And so what we need to check is that the largest or the smallest non-zero eigenvalue, the largest lived relaxon, is associated with an odd eigenvector. That is the condition for driftless second sound as proposed by Hardy. And what we find here is that that condition is not satisfied. So what we're proposing is that driftless second sound does not occur between at least 50 Kelvin and 300 Kelvin in germanium. So that leaves this other type of second sound that was used as a catch-all by Hardy and ultimately requires solving for a given geometry the linearized Boltzmann transport equation without making an assumption about a wave-like solution to that geometry. So we can do this, and we're doing it for a case of a point source in space and a periodic heating in time. We're looking at two temperatures here, and we're looking at the solutions from the hyperbolic heat equation, the linearized Boltzmann transport equation, and the diffusion equation for different heating frequencies. All right, so I'm just have this non-dimensional parameter for frequency that we're looking at. And we can see for across a wide range of frequencies where we are in the diffusive regime going all the way to the ballistic regime, we do not observe resonances in our LBT solutions. On the other hand, resonances are indeed observed in the hyperbolic heat equation. So this sort of leads us to the question of the validity of the hyperbolic heat equation over the linearized Boltzmann transport equation. Now let's look at what a material wherein a second sound is expected to be observed and what sort of predictions would the LBT make for this geometry for that material being graphite. And indeed, what we do see, if we do this geometry, if we use this geometry of a periodic source in time and a point source in space, we do indeed see resonances in graphite at a temperature of 100 Kelvin for frequencies that are achievable in the FDTR geometry. And this is dual to the observation that we've observed in the TTG at 80 Kelvin and above for graphite, where we do indeed, if instead we have a point source in time and periodic heating in space, we still see resonances, right? So you can think of this, these two heat geometries as kind of dual to one another, right? Where the overall temperature wave would actually behave much like a plane wave. And so this is a nice material that should be considered as a short-term case study of hydrodynamic transport in the FDTR geometry, right? And I point out that graphite, hydrodynamic transport in graphite has not only been observed in TTG, but in other geometries as well. And it would be nice to see the study of graphite in FDTR as well. So what about an actual FDTR simulation? For that, we turn to the relaxation time approximation of the BT and restrict ourselves to 1D geometries. What would the RTA predict for a given phase relative to the diffusion equation and to the hyperbolic heat equation? And what we find is that the RTA is capable of predicting a wide range of phases for a given set of initial conditions. What do I mean by initial conditions? Well, I mean that the initial population of non-thermal phonons that essentially drive the heat transport, your initial T0 that drive the heat transport, is undetermined. And typically we use something called the thermal heat distribution, which is simply the relative contribution of a given mode is determined by that mode's specific heat. And that seems to work well for many experimental measurements, but it's not always the case. And we have seen this in other materials like silicon and diamond as well. And it's understood that there is a complicated process that's leading up to this initial non-thermal distribution in the phonon population, that being the exchange between the electronic degrees of freedom and the phonon system, and how exactly that exchange takes place is still an ongoing area of study, right? It's a very computationally intensive task to accurately model that. So at this stage, we still can sort of arbitrarily choose this initial condition. And the exercise here is that we're showing that if we choose different conditions, we can reach different phases for a given frequency. So this leaves a lot of room in the tunability of the RTA solution to model the FTTR experiment. Now, the flip side to this is that it makes it very difficult for us to actually rule out the RTA as being incapable of modeling the phase for a given experiment. And to have an unambiguous signature of second sound requires the elimination of the RTA solution or RTA approach to the BT as being able to model the experiment, right? So we need to see strong deviations from the Fourier temperature profile and strong deviations from the relaxation time approximation profile as well. This needs to be addressed when claiming second sound. So we have this theoretical discussion about the question of second sound, but we've also begun our own experiments using FTTR on transducerless germanium. And what we're observing at this point in time is that we find that the diffusion solution or the hyperbolic heat equation alone is not enough to explain what we're observing, but rather that one must include the impact of carrier population and its contribution to the reflectance signal. And we're seeing this not only in germanium, but also in silicon and gallium arsenide. And I would like you to, I'd like to point out that to see more about how this is done, please check out Qichen Song's talk at MRS Spring, wherein this is discussed in some detail. So with that, I would like to conclude and remind ourselves of the key takeaways here, that being that the LBT calculations today do not predict second sound in germanium. The RTA-BT point out that phase lag alone is not a sufficient observable for claiming second sound. And our preliminary experiments on transducerless germanium indicate there is an impact of carrier effects that cannot be neglected. So with these takeaways, we can turn to some questions. I would like to see the study of second sound in germanium in an entirely different geometry. And that would sort of lead to some robustness of this claim, as well as there being some different materials such as graphite in FTTR, and how do those hydrodynamic signatures differ or are shared? And finally, what about the TTG, and why is it that we see a drifting second sound but not a driftless second sound or another type of second sound in TTG? So with that, I will take any questions that you may have, and thank you for your time.